Hello everyone, welcome to lecture number 40 in this NPTEL course on Riemannian geometry. So, in the previous lecture I proved that I introduced this notion of minimal geodesics, which basically means that if you are given 2 points P and Q, you have the shortest path between P and Q, that is called a minimal geodesic between P and Q. So, and then we showed that all geodesics are at least locally length minimizing. Okay. So, in this lecture I now want to introduce a metric space structure on Riemannian manifolds. So, I will first introduce the distance function. Okay. So, for any points P and Q in M, we let the distance between x and y be the infimum over all admissible curves connecting P and Q of the length of sigma. Okay. So, note that omega PQ is obviously non-empty. So, the infimum is makes sense. So, the infimum is well defined, since the length is always a non-negative number, right. In fact, we will see shortly there is going to be a strictly positive number. So, the infimum is I mean the lengths are basically lower bounded and it is a non-empty set. So, you can always talk about the infimum. Okay, and then a remark is that a curve gamma is minimal then if and only if the length of gamma is equal to this d of p comma q. Okay. So, our goal is to actually show that that this D defines a metric space structure on M, right. So, that is the next sort of proposition. Okay. So, so I want to claim that MD is a metric space. Okay. That is, D satisfies the following properties of being a metric. It is symmetric, which means that D of x comma y is D of y comma x. It is positive definite, okay. That means that if you take 2 points, the distance is positive, the d of x y is positive whenever x is not equal to y, right. And third, it satisfies the triangle inequality. So, that means for all x, y, z, the distance between x and z is less than equal to the distance between x and y and the distance between y and z. Okay. So, why is this the case? So, let us, the first one is completely trivial, right, because if you have a path from x to y, you can always reverse that path and you get a path from y to x while preserving the length. So, this function D is obviously a symmetric function. Why is it positive definite, right. So, so suppose we have a point, suppose we have 2 points P not equal to Q. I want to show that that if you take paths between P and Q, the lengths of those paths cannot get arbitrarily close to 0, right. That will show that your function D is positive definite. So, to that effect, let U P epsilon be a geodesic ball around P of radius epsilon such that Q does not belong to UP epsilon, right. One can always do that because I mean our manifold is in particular Hausdorff. You can always find an open set around P that does not contain Q, and then you can find a sort of geodesic ball that's contained in that that open set, right. But then for any sigma connecting P to Q, say sigma is from 0 to 1 to M, sigma of 0 is P, sigma of 1 is Q. So the picture is the following: you have your P, you have your Q, you have this geodesic ball here. Now suppose you take any path connecting P to Q, there is a sort of first time where the path will leave the geodesic ball UP epsilon. So there exists a T naught such that T naught is the first time when sigma leaves UP epsilon, or equivalently if you take sigma of T naught, that is the first time, so that this belongs to the boundary of the geodesic ball. But then we have already seen that that the radial geodesic between these 2 points is going to be shorter, right. So then clearly the length of sigma will be bigger than or equal to epsilon, but this happens for all sigma. So that means that the infimum over all sigmas connecting P to Q is going to be bigger than or equal to epsilon, which means that the distance, this function d of P comma Q is going to be at least epsilon, so it can't be 0, right. So this proves positive definiteness. The triangle inequality is again an easy exercise. I'll leave that easy, but a good exercise for you to do, so that I mean the idea is the following, that suppose you have these 2 points xz and y is some other point, then a way to go from x to z is you consider paths via y, right. So the paths that go via y form a subclass of the paths from x to z. So if you take an infimum, the infimum will be smaller than the infimum over the lengths of paths from x to y plus the lengths of paths from y to z. So that is essentially the triangle inequality, okay. So I'll let you fill in all the details. Okay, so the next thing I want to do is I want to define the metric ball. So we have now a notion of geodesic balls using the exponential map. When we learn about metric spaces in first course in point set topology or analysis, we talk about metric balls all the time. So let me remind you of the definition. The metric ball of radius epsilon centered at P is basically given by, so the notation is B of P comma R, sorry, of radius may be R. So this is the set of all points x in M, so that the distance from P to x is strictly less than R. So this is by definition this is always an open set in the metric space topology, right. So here's the key sort of proposition. So let UP epsilon be a geodesic ball of radius epsilon centered at P, okay, then UP epsilon is in fact the metric ball of radius epsilon, right. But one key difference is that metric balls, for metric balls your radius r could be arbitrary, right, but for geodesic balls, because they are sort of diffeomorphic images of the exponential map, your epsilon can a priori only be in a small range, right. So it can be only between 0 and some small number, okay. So the second key point, see we have our manifold M which already comes with a topology, right. I mean that is part of the definition. A smooth manifold is a topological space which is Hausdorff second countable and with this sort of locally Euclidean property, right. So M obviously comes with a topology. Now we have a metric on M, a distance function on M, so that obviously induces its own topology, right, where that particular topology using the distance function has these balls, the metric balls as a basis for the topology. A priori there is no reason for these two topologies to be the same, but in fact our Riemannian manifolds are nice enough that that these two topologies actually coincide. So the topology of M with this distance function coincides with that of the topology of M, okay. So in particular the distance function is continuous, right, because the distance function is obviously continuous in the topology induced by the distance function, but here we are seeing that topology coincides with the already existing topology on M, hence the distance function is continuous on the already existing topology on M. Okay. And the third part is that if you look at the closure of one of these metric balls, then that is precisely the set of all x, so that the distance function is less than equal to r, okay. So sometimes we denote this set as b less than equal to r of p, okay. So just a quick remark, the third property 3 is not true for general metric spaces. Okay, so for instance, I mean it's a nice fun exercise to come up with examples. You can, I mean a hint is you can just take the discrete metric, right. Then I mean you can cook up examples where the closure of this ball is basically the singleton set P, but the set on the right is actually the whole space, right. So you can cook up a discrete metric on any topologic on any set, so that this holds and so that this equality is actually not true, okay. Right, so let's prove. So proof of proposition. Okay, so one is easy because radial geodesics, since radial geodesics are minimizing. So one can I mean I'll leave this as an exercise for you to write down the details of the proof. Let's prove part 2. So the first claim is that these open balls are actually open in the existing topology on M. Okay. So again, of course, we know that it is open in the metric topology, but on the existing topology on M as a smooth manifold, I want to claim that B of PR is open. What is the proof? So let Q be a point in this, and let us say epsilon is small enough such that the distance from P to Q is less than R minus 2 epsilon. Okay. So we know that the distance between P and Q is less than R, strictly less than R. So one can just squeeze in a little epsilon gap between the distance from P to Q and R. So but then consider the geodesic ball of radius epsilon around Q. So let X be some point in this geodesic ball. Okay, so then clearly the distance from Q to X is less than epsilon. Why? Because the radial geodesics are actually minimizing curves from Q to X, and so then because this is a geodesic ball of radius epsilon, the distance from Q to X has to be less than epsilon. But then by the triangle inequality, if you estimate the distance from P to X, that is going to be less than the distance from P to Q plus the distance from Q to X. The first one is less than R, the first one by choice is less than R minus 2 epsilon, and the distance from Q to X is less than epsilon. So the resulting thing is less than R minus epsilon, which means that X is also in the ball of radius R around P, the metric ball of radius R around P. Okay. But this was true for an arbitrary X, which means that this entire geodesic ball is contained inside this. Okay. But this is obviously an open set, it is a diffeomorphic image of an open set in the tangent space. So given any Q, we have found an open set contained around Q contained completely inside this metric ball. So this implies that the metric ball is open. Okay. Alright, now how do you prove the third part? So clearly, if you look at the set of all points whose distance function is less than equal to R from P, then that is clearly a closed set because the distance function is continuous by the second part. Okay. So then the closure is by definition the smallest closed set containing B of PR. So this implies that the closure is contained inside this. So if I am to show that these two sets are equal, I have to show the reverse inclusion. So for reverse inclusion, let right, so let Q be a point here such that the distance of PQ is exactly equal to R. If it were less than R, then there is nothing to prove, right, because then obviously it would belong to the closure of the ball, of the metric ball. So let us assume that the distance from P to Q is exactly R. Then by the definition of the distance function, right, for all natural numbers k, there exists a unit speed curve, call it gamma k, from 0 to R plus 1 by k, or maybe I should say 0 to Lk, such that gamma k of 0 is p, gamma k of q is gamma k of Lk is q, and Lk is between r and r plus 1 by k. Okay. Okay, so let so the point is I have one of these gamma k's. So let let me on the picture what I do is I take a point here which is very close to q. Okay, so let qk be equal to gamma k of Lk minus 1 by k. Okay, so then the distance from q to qk will obviously be less than the length of the part of gamma which connects qk to q, because you know by definition the distance is the infimum over all possible paths connecting these two. So this is obviously going to be right. So so maybe for safety I should yeah. Okay, so this is going to be less than 1 by k, which is which of course goes to 0. So which means that qk's converge to q. So now the second claim I want to make is that that qk's actually belong to the open metric ball. So for that I have to estimate the distance between p to qk. Well, sorry, I should maybe right. So maybe I should have a strict inequality here, right? Okay, so so the distance from p to qk is less than equal to the length of the part of gamma from 0 to Lk minus 1 by k, but this is a unit speed curve. So this length is precisely Lk minus 1 by k, but by our choice that's strictly less than r, which means that qk's are points that are contained in this. Okay, but they limit to the point q, which means that q has to be in the closure. Okay, so that completes the proof. All right, so that's as far as the distance function is concerned. In the next couple of lectures I will explore the notion of completeness for this metric space. Okay, so we have of course from our usual metric space stuff, we have a notion of completeness using Cauchy sequences. I will give a Riemannian geometric characterization of that completeness. So that is the famous Hoff-Reno theorem. So that will be the content of the next couple of lectures. Alright, so that is it for now. Thank you for your attention, and I will see you next time around. Thank you.